How the fuck are you? Stoner Dave here, and I've just watched probably the most inane conversation that I've ever watched on YouTube in my life. Okay, I guess it's not a conversation, it's a monologue really, but so it's a video by this guy named Detroit Wrecker. They put up about I guess about 4 months ago, according to the date on the video. And he's talking about modding amplifiers. Says you shouldn't modify your amplifier. If you want more gain, just put a distortion pedal or an overdrive pedal in front of it. Bada bing, bada boom, problem solved. Woo, wait. Oh my goodness. Very tear to my eye. So, whew, that was a good hit. So, in watching Wrecker's video, I'm getting the idea he doesn't really know what gain is. He talks about I play with a lot of gain, a lot of distortion. So he seems to be under this impression that gain and distortion are the same thing. I can understand the reason why, and that's because typically with amplifiers, your gain section is attached to your dirty sound, your crunch, your overdrive channel, right? Your your clean channel doesn't seem to have much as far as a gain control. It has volume controls, but no gain controls typically. And that is the reason why people want mods, because they want more gain in their clean stage. Overdrive and distortion are well, overdrive and distortion are different things, but gain and distortion are different things. So a lot of times you'll turn your gain up and you'll notice an increase in volume. It gets louder as you turn the gain up. Gain is something, it has to do with how much it's amplifying the incoming signal. So, I don't know what the RMS values are from a guitar output. So I have to make that shit up, right? So, if we have a guitar that's outputting 100 millivolts RMS, and that signal goes through an amplifier and it comes out and it has an RMS value of 1 volt, right? So it's that signal's been magnified 10 times. It went from 100 millivolts to 1 volt. That's 10 time magnification. That's a gain of 10. Now, we usually talk about gain in decibels, which would be basically we take that factor of 10, we take the logarithm of 10, and then we multiply that by 20, and that gives us our gain for this particular situation. It's not always, it's always whatever that gain is. You take the logarithm of that gain, multiply it by 20, and that's your decibels. It's it's kind of weird the way they do it, but it's the reason why it has to do with how we calculate power and voltage and resistance and all that shit using Ohm's law. That's where the 20 comes into. You know, it doesn't really matter how we got that conversion from gain to decibels, but That's what gain is. It's how much is the signal being amplified or multiplied. That's your gain factor. Distortion and overdrive isn't about gain, right? That's about clipping. Now, the reason why you can't just say, well, I want more gain, put an overdrive pedal in front of it or put a distortion pedal in front of it. Overdrive and distortion pedals have a stage of their circuitry called a clipping circuit. It's essentially, it's as simple as two diodes put in parallel and opposite directions so that they, one is forward biased and one is reverse biased. And what that does is once the voltage goes above a certain point, any voltage above that goes to ground. So the output signal will look like the start of a sine wave with a flat top. And then when the voltage of the signal goes below that thing, it'll start going as its normal path. But while it's above that diode voltage, the forward voltage of that diode that it's going through, it'll just maintain that voltage and be just a straight signal, almost DC for that segment of time. Then when the downward portion of the cycle starts, once it goes below that forward voltage of the diode, the regular signal will come in. Then you start going into the negative zone. That reverse bias diode is now forward biased. And for its forward bias, as we go lower in voltage, it's getting more and more forward biased. Once it goes to that negative value that's equal to the forward voltage of that diode, it'll clip it, and everything above that will go to ground, and it'll just go like that until the voltage starts going up again. So what you end up with is this sine wave that has flat tops and flat bottoms. It's clipped. That's what a distortion and overdrive pedal does. Now, yeah, there's a bit of gain that goes along with that. And depending on how you adjust your settings on your pedal, you may be able to get it to work as just a boost. You know, it gives it a little bit of an extra boost. And that may work for what you're trying to accomplish. But if what you're looking for is a nice, clean signal that has a lot of gain going on with it so that it gets more power going out of it, whatever you're trying to do. If you need more gain in your clean stage, you can't just put a pedal in front of it. Unless that pedal is just a fucking boost. That's a clean boost, not a fucking overdrive or distortion pedal. A clean boost. And they don't make a lot of pedals like that because people don't usually need that, right? Usually they'll just get a higher gain amp if that's what they need. You know, this amp's only 50 watts. I need 100. But if what you're needing is just a little bit of extra oomph on your clean station and your clean channel, a mod is the only way to do that. Either that or else get a whole new amplifier. So, another thing that he was talking about was that, you know, all the amps that he's looked at, they've all had either this Fender style or this Marshall style. And yeah, that's understandable. And you'll understand if you look closer at those schematics. They're actually the same thing, just they have the gain stages put into different locations on it. They all have the same thing going on at the end, some power tube amplifying everything to a speaker, right? It's the gain stages before that, the pre-amplification, that may be different. But again, you look at them, they're using different tubes maybe. They have different ratings on those tubes. No big deal. The schematics itself, they're almost identical, except for, like I said, they may have tone going on here instead of over here and that. But at the end of the day, they're all doing the exact same thing. And let's be honest, they're all working with the same set of conditions. They want to amplify a guitar so that it sounds good. Y'all are the ones that decide what sounds good, right? Not them. But at the end of the day, yeah, there's only so many different ways that you can assemble these components and get a signal that works. You change different values of capacitors. You can throw in an inductor and whatever. You know, you could do all these different things. But at the end of the day, there's only so many ways that you can put these components together, and they're going to work in a way that's satisfactory to what you're trying to do. Now, you said you've been working in electronics, trying to learn how to work on these tube amps for like 6-7 years. That's a long fucking time. That's a really fucking long time. I'm a completely different person than I was 6-7 years ago. I mean, we're in a completely different world than we were 6-7 years ago. 6-7 years ago, the idea that fucking a virus could fucking put us on the brink of catastrophe was unthinkable. 7 years ago. Seven years ago, Republicans could actually claim that they gave a shit about America instead of saying they're trying to fucking conquer it. I don't want to get political. Needless to say, there are reasons to get a modification to your amp. If you need more gain, if you need more gain on your clean signal, you need a modification. If you want to adjust your bandwidth, right? So like, say you're in some super heavy metal group that tunes super low down, so like you're 5 octaves below E, right? Your amplifier has a bandwidth, right? And that bandwidth is determined by the amount of gain that you're getting. So if you increase the gain, you're going to shorten the bandwidth. Increase gain, shorten bandwidth. Now, you've increased the gain, so you've shortened your bandwidth. But now your guitar that's over here is well outside outside your region of bandwidth because you tuned down so low. So what do? Well, you're going to have to go in and change some capacitors and some resistors so that you can adjust this bandwidth over here. That's a modification. So you need to adjust your bandwidth because you play so low. You want to keep your tone crystal clear and you want to sound like whatever it is you're trying to sound like. So to keep your sound at a gain level that's appropriate, you need to adjust that over. Because if you're a typical Bodhi plot, right? See if I can find a Bodhi plot is just so a typical Bodhi plot. We'll pretend my hands are the end. So a typical Bodhi plot goes like that. You see that little line going from my fingertips? That's your typical Bodhi plot, right? So frequencies over here. If you're below this frequency, the output drops off. So you're dropping off as your frequency goes lower. Same thing happens over on the positive end too. You know, if you're above this frequency, you get less and less output. And where that Bodhi plot goes on your frequency really depends a whole hell of a lot on how much gain you have. Less gain, bigger Bodhi plot. More gain, smaller Bodhi plot. And that point between my fingers there, that's your area that you can play in. Now, you guitar players that tune in standard tuning, you're the ones that these guys are all designing for, right? So when you start tuning down, right, and moving your frequency over this way some, well, what happens is your gain starts to drop as you go down lower. Now, the thing is that these heavy metal bands, right? They've been tuning down a lot, right? I think I've seen a thing where Zakk Wylde goes to low G or something like that. That's fucking low, right? Like your open E note on your low string, I think, is only like 56 hertz. 60 hertz is a one that we all know about because that's the cycle of noise. So you see why these guitar amplifiers back in the day, they started having so much problems with that 60 cycle hum, because everybody was fucking setting their amplifiers to have a peak resonance around that 60 cycle. So when these guitars were picking up the fluorescent lights and that 60 cycle hum comes in there, it's like fucking right at the peak where fucking everything goes shining through. It's like, oh, all I hear is that fucking 60 cycle hum. God, get that off of there. Drove people nuts, right? But it was the sound that came through the clearest because it was the sound that had that peak going on. It was closer to the bottom end of the body plot, but still it was right in that peak range, like perfectly in that peak range. And that's why it got to be such thing. And people, they tried to say, and what would happen is they would sacrifice the low end of the guitar to try to get rid of that hum. And what eventually ended up happening, somebody just said, hey, why don't we just get something that'll cancel that out? And they put a humbucker in there. They created the Humbucking Pickup, which was essentially 2 single coils slapped back to back. They're like, so it amplifies the signal, and it really does. It works because of the way that they're working opposite of each other. The two opposing things are on the going the other direction, but because they're of the same, they double magnitude. And it's like fucking the 60 cycle hum, because it's going the same direction in both pickups, ends up getting canceled. It's crazy. So when you look at the signal going from these guitars, right? Understand, right? This signal is going through a pedal. It gets processed. Doesn't matter what kind of process it is. I'm a huge fan of analog, and with the way that digital has been progressing, digital is like damn near indistinguishable from analog. But I like the analog because I can better explain how it's working compared to digital, which I only say is like it's modulating the pulse width. And it's like, well, what's that mean? Well, it's kind of changing it depending on how. And it's like, well, fuck, man. It's like you have to go into a whole dissertation about fucking digital signal processing, whereas analog is like, well, it just kind of amplifies it. It amplifies it because of this. And you're like, that's pretty simple, pretty easy. Analog is simple and easy. That's why it works so well. Digital can become complex, but it's reliable. Analog, susceptible to like any changes that happen. Like it'll affect the analog signal. Like fucking say there's some noise in the atmosphere, right? There's always noise in the atmosphere. But say you're in a really noisy environment. The analog device, when that noise comes through it, it doesn't know the difference between that noise and the signal itself. So it'll amplify that noise if it comes into it. Whereas the digital will recognize that that's not acceptable, and it'll kick that noise out very easily. So while I was thinking about this, I got to thinking, because he's talking about he wants to do tube amp repair. He's learning about this stuff to learn about tube amps. Which brings up the reason, why do people prefer the tubes over the solid state? Solid state actually isn't digital either. There's a lot of analog solid state shit out there. But why do people prefer the tubes over the solid state? I'll tell you why. Tubes are, when you get to that breakup area, tubes are a bit more random than transistors. Transistor, you get to that break-off area, it doesn't matter. It's clipped. It's clipped. You have to go, once you go above it, you have to come a bit below it before it'll unclip. Makes it so that it's got a very static sound. You'll hear people oftentimes will refer to solid state as having a cold, lifeless sound. It's because that clipping is so steady. It always clips at the same point in the signal all the time. Tubes, on the other hand, when they get to that breakup area, it's kind of random whether it'll clip or not. Sometimes it'll clip, sometimes it won't. You have to go well above that little breakup region to get it to do a solid straight clip. Same thing with once it clips, until you get well above that, it doesn't always clip there. It'll clip here, sometimes a little bit above, sometimes a little bit below, which makes it very random, and that makes it sound more organic, more lifelike, more like something you would hear in nature, right? That's why people prefer the tube amps. Now, the interesting thing to point out is that why we use tube amps, because if the world had evolved differently, we probably wouldn't even have tube amplifiers for guitars, right? If the transistor had been invented maybe 5 years earlier, there wouldn't be tube guitar amplifiers. The reason we have them is because if you look around, like the first signal amplifiers, like a radio, right? The first guitar amplifiers was just plugged into a radio. They just took the antenna off and hooked up the output of the the output of the pickup to where the antenna goes into the stereo, and they started playing, and it worked. And that was the first guitar amplifier. It was just a modified stereo. But back in those days, stereos weren't with transistors and op amps like they are today. Today you can get a stereo your cell phone has a fucking stereo built into it, we have them that small, right? So back then they had tubes. They had to use tubes, vacuum tubes, which means that it's like big ass fucking stereos, So when the guitars was invented and they said, well, we need an amplifier. Well, what are you going to do? They fucking looked at the stereo. They said, okay, let's take the stereo right here and put a guitar input on it right here. Bada bing, bada boom. Your stereo already has a tone knob on it. It's got a fucking volume. All they had to do is just get something to adjust the gain eventually. Then when the humbucker came out was actually when people started noticing that they'd get a lot of distortion and clipping on the signal with the higher input power, because the extra pickup almost doubles the output. So it's like, wow, this sounds amazing. And that's how the modern guitar amplifier started to grow. See, I'm not a guitar player. I always wanted to be a guitar player. I bought guitars and amplifiers because I wanted to be a guitar player. Problem is, I'm a stoner. Lazy. The ethic that it would take for me to actually learn to play a guitar and become a guitar player, too much. Too much. But I've always been interested in electronics since I was like knee high to a grasshopper, you know. And trying to learn to play guitar, I saw so many pedals and amplifiers and so much electronics. Like, this shit was just amazing, right? So I started looking at schematics and opening up the pedals, seeing what's making them breathe and drive, and then I start buying books, right? Then I go to college. They're like, well, what do you want to be? I'm like, well, I want blah, blah, blah. I don't know what I want to be, blah, blah, blah. I start taking all these classes on math and physics, and then came the study of electricity itself, right? Once I got into that, and that shit was just phenomenal. I mean, I took other classes while I was there too, you know, political science, ethics, all these little things, because you have to fluff up your fucking profile, you know. You can't just say, yeah, I went in there and fucking took fucking all these math and science classes and blah, blah, blah. You can't get a degree with just math and science. If you could, I would have had 2 of them. Oh, wait, I do have to. I'd have 5. But, needless to say, learning this stuff isn't really as hard as it seems. You know, I have a schematic right here for a basic overdrive pedal. So, and I was basically wanted to show is that what happens when you try to put a pedal in front of your amplifier to get more gain. So, I'm just going to use this schematic right here. So let's take a look at that. All right, so this is our schematic for our pedal, right? You can see there's a 9 volts right here. There's a 3.3K ohm resistor right here. There's a 50K potentiometer. It's a basic potentiometer, 50K, going down here to a basic, looks like an NPN transistor. There is a 2.2 mega ohm resistor biasing this thing here to our base input, right? And we have a 680 ohm resistor going down to ground. So our audio signal will come in through here, hit this capacitor. This is a 47 nanofarad capacitor. It's not labeled. I should have labeled it, but I didn't. But I've memorized the schematic, so no big deal. This capacitor is what's called a coupling capacitor. It's a coupling capacitor. I didn't bring a pencil with me. Damn, I should have. Because I've noticed that you seem to have some confusion over what the difference between what capacitors are and what they do, right? So this is a coupling capacitor, and what it does, it couples this signal going in to this overall transistor and what it's doing. All of our gain and output and everything is going on here. All of this is just amplification. This signal here, I don't know what a guitar puts out. Maybe as low as 50 millivolts, as high as maybe 500 millivolts. I don't know. But I know it couldn't be much more than that because the way these transistors operate. But anyways, so this signal comes in here. Now you can see this is a very high resistance, so it's not really going to do anything. This right here, what this capacitor does, because there's some DC circuit going on here, it keeps that DC here. This capacitor here actually prevents DC from going over to here, but the AC signal goes right through here. This is another coupling capacitor, couples that AC signal to the output. It also could be referred to as a blocking capacitor because it blocks out the DC from this battery and or power supply. Okay? Now, This is the reason why you can't just plug the pedal in front of there. If it was just this, you could do that. You could plug this into the amplifier and you would essentially have a big boost in gain that you can adjust by turning this knob. But this right here is the reason why you can't just plug a overdrive pedal or a distortion pedal into it. Now this is, I'm assuming, a typical overdrive pedal. I've seen a lot of different schematics. A lot of them will have a op amp instead of a transistor here, because the op amp will prevent noise from going along with it a lot better than this transistor will. This transistor is not just going to amplify my signal, it's also going to amplify any noise in the signal. That's why your overdrive pedals typically will come inside of a metal cased box, right? This is not an overdrive pedal that you'd be able to put inside of a plastic container like those really cheap ones. This would have to be in some kind of a metal box, because that metal box acts as a Faraday cage and prevents noise from getting to the signal. All right, so that signal is going to come here, and we see that there's a split, right? So there's a resistor here, 33K resistor, that then has a capacitor, an LED that has its I believe it's the cathode, no, anode. I forget. It's got its negative, the N side, because it's an NP transistor or PN transistor, depending on the N portion is facing towards ground like it should be, and it's identified on schematic by this line right here. On the transistor itself, the leg with the flat side will be this side, unless you're using a surface mount, which would be identified with a marking on there. And this is another LED, can be the same or different depending on what you're trying to do, but it's got its N, P are reversed, so ground is on the P position of the diode junction. And then of course this signal goes across the top of that to ground, so this acts as a low pass filter. So what that means is that low frequencies will continue across this line here. High frequencies will go past this, through this capacitor to ground, not making it to the output. This LED, typically LEDs have 1.2 to 1.7 forward voltage. So what happens is on the top portion of the signal at this point, once it gets above that 1.7 volts, it'll go to ground. It'll go through here and go to ground. The LED typically won't activate because it's such low current, but the voltage will be enough that it'll stop, and it'll clip the top of that signal for anything above that voltage. Same thing here, but when it's negative voltage. So on the downward portion, once it gets above that 1.7 volts or whatever it is, that'll go down to ground, and anything, and then when it swings back up, it'll go, so it'll have a clips. So because these are LEDs and they have a higher voltage than these right here, which are just your typical switching diodes, the LED, because the signal typically has, your input signal has a curve to it, like that, right? So because it has that curve to it, and the voltage is clipping up here, you'll see that this signal will have a bit of a rounded to the top before it clips. And that's the reason why the LEDs are used here instead of typical clipping diodes. Now, on the other side here, from this capacitor, we have another capacitor, which has a resistor going to ground, a switching diode, which is just your typical diode, forward voltage of about 0.7 volts, and another diode, which is reversed compared to this one. So as you can see, the PN junction goes PN here, and here it goes PN. So on this side, when the voltage gets above about 0.7, 0.6, it's going to hard clip. And when it gets below that voltage, it'll start signal again. So again, we're going to have what looks more like a square wave on this side. Doesn't really matter because these two are going to blend inside this potentiometer. come out here. So it's going to have some of this rounding, some of this hard clip. And how you adjust this will determine where it goes which. So we have the low pass filter and the high pass filter running in parallel to this potentiometer, which means that we've essentially got 10K of resistance here plus the parallel configurations of these right here. So nice there, right? Which is going down to this, which is a 100K audio tapered potentiometer. Goes here. Now on this side, you see this is going to ground, this is going to ground. So what this is doing is actually this potentiometer is determining how much of our signal is going to go straight out and how much of it is going to get stopped by here. So when we go down here and we're down here, you think about that, it's the signal goes down here, and down here we're getting 100% ground. Up here we get like 50% of the output signal, and it's basically just a voltage divider circuit. Down here it's 0, up here it's 100, so you just get a percentage of that. And it's on an audio taper, which means that it's not logarithmic. It changes depending on where you're turning it. And it's the way it works is that 0 is 0. You get to 1, you have whatever that percentage is, right? Doesn't really matter. We're talking about logarithmics. When you go to 2, 2 is going to be double what 1 is, right? 3 will be double what 2 is. 4 will be double what 3 is. Yada, 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 until you get to the end. And that's why when you look at it, it seems to change slowly at one point, then really fast after you get past a certain point. It's because, 1 to 2 isn't that much, but 2 to 4 is a bit much, and 4 to 8 is a lot, and 8 to 16. So if you look at it rather, because here we're cutting rather than adding, but it's kind of the same way. We're just doing it in reverse, right? So it goes from to half, to quarter, to an eighth, to a 16th, all the way down till you get to 0. And at 0, it's 0, C'est la vie. But this whole part right here, this is what adds color to the signal, right? And you look at it, well, you got capacitor, 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 resistor, 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 resistor. This resistor, we don't need to worry too much about it. This is really setting up our output impedance. This right here and this right here work together to form our output impedance. But that's all it is. It's setting up our output impedance. We're going into, typically we're either going into another guitar pedal or an amplifier. We're looking at a high input impedance, so we want a high output impedance here so we can get maximum power transfer, because we're still transferring from the guitar. What we've done here is we actually, because we know we're going to lose some of our signal going through here we're going to get what's called voltage drops. Signal can't pass from one end of a resistor to the other without some kind of a voltage drop. So we add voltage here, lose voltage, and we are wanting essentially something that has a voltage not much higher than the voltage that is coming out of here. You say, well, we want to clip. It's already clipped. So when the amplifier sees that signal, it's seeing a signal that looks a lot like what an amplifier looks like when it's breaking up. You're getting this rounded clipping here with the LEDs. You're getting this hard clipping here with the diodes, and we're getting that mixed together here. So we're getting an output that's got kind of a blend of both of them, just kind of depending on how we've got this set, right? Changes the shape of our tone. I really should just show y'all what it means by tone shaping, because y'all would be astounded by what it really means, Because when I first started hearing these terms, like before I started going to school and stuff, I heard clipping. Like, I don't get it. What does it mean, clipping? Then, you know, when I went to school and I learned this stuff, it's like, oh, I see. That's crazy. And it's hard to explain, but I could draw a diagram maybe that would show you why your guitar signal looks the way it looks when you look on it, like on an oscilloscope, and when you hear it, because it is really bizarre how it works and why it gives you that tone that it gives you. But in the meantime, check out this schematic here, and I'll do more videos on this here so you can see what it looks like and everything like that.